Okay. All right, great. So our next speaker for the workshop is going to be Dr. Rakesh Baba. He's from Oregon State University. And if you remember, Asfa mentioned the CyberCore SFS program yesterday, which is now active here at WSU. I met Rakesh through that. He's sort of WSU's mentor because their program's been around for a couple of years and ours is brand new. But Dr. Baba is an associate professor at Oregon State University School of Engineering and Electrical Engineering, Computer Science. He's got over 15 years of experience in cybersecurity research and education. His research interests are in the design of secure and trustworthy networked and distributed computer systems. He is the founding associate director for two groundbreaking cybersecurity education projects at OSU, one being ORTSOC, the nation's first cybersecurity teaching hospital, and the other being the Oregon Cybersecurity Center of Excellence. I tried looking up what ORTSOC stands for, and it says it's actually not an acronym anymore. Okay, so I don't know, maybe you can know what that is, but anyways.
Thank you, James. Good afternoon, everyone. I wish I could have been there in person. It's just that OSU is on a quarter system, so our quarter is still happening. We finish mid-June. So maybe next summer I could be there in person. Thank you all for being here for the talk. I will jump into the research talk, and maybe if you have a few minutes in the end, I will pull up a couple of slides on our ORTSOC. Just for since just not to leave you hanging. It's think of it like just like medical profession students studying to be medical professionals have to go do a residency or in a hospital to get hands-on experience of how to diagnose and treat patients. This is similar for cybersecurity, where we have a security operations center, and our students in our fourth year spend 10 hours a week in the operations center doing different, learning different skills through clinical rotations. It's, for example, network security monitoring, penetration testing, security assessment for real organizations. We have about 14 client organizations right now, including 3 or 4 small cities in the region, couple of education service districts. So basically IT functions for school districts, and so on. So if I have time, and if you have questions, I'll maybe pull up a few slides up there. But today I thought I'll talk about this research work we started about almost 7-8 years ago. We still have offshoots of this research happening, but a bulk of the work was completed 3-4 years ago. But this is an accessible. I felt this would be an accessible topic for this workshop. So without further delay, let me jump in. I'm covering 2 papers here, and so at the bottom I have the pictures of all my co-authors on this. I realized I'm missing one of my PhD students. The first person on the bottom is Arzu Rajabi. She is the lead author for the second part of the talk, and the person in the second picture at the bottom, I don't know if you're able to see my cursor or not, is Kimia Tajik, who led the first part of this work in the first part of this talk. Okay, and there are follow-on works being taken by completed by Brandon, who is the third person here. So anyway, so what I'm trying to say is a lot of the credit, I'm presenting the work here, but it's joint work with a lot of collaborators. Okay. So just a little bit about myself. James already mentioned I have this broad umbrella research term that covers a lot. But in the past few years, these are the 4 broader areas I've been focusing on. Real-time system security. You actually have a faculty member there who is an expert on this, Dr. Munawar Hassan. Did a lot of fantastic work, and I had the privilege of working with him when he was a PhD student. I also do a lot of cybersecurity work for electrical grids. WSU has one of the strongest uh, electric power engineering programs in the country, and you have a lot of fantastic faculty. And I had the pleasure of working with some of them over the years on different research projects. But in these days, because of the OTSOC work, where we have students doing clinical rotations in a security operations center, I'm sort of slowly shifting my focus to more towards enterprise security work. Sorry, I realize I have a typo right here. Um, but but today I'm going to talk about usable security and privacy focus. But I just want to tell you there's a broad topics that I split my attention on. So I'm going to skip this, and since I've already given an overview of that. So what's the challenge with usable security and privacy? Designing good security systems in itself is challenging, but making them usable is, compounds the challenge. And if you don't make security systems usable, then people will be less likely to want to use them, or they will not use it correctly, or they're likely to try and bypass those systems. And so it's really important that we design security mechanisms or privacy mechanisms that are usable and acceptable for end users. So in this particular talk, I'll focus on, balancing image privacy with usability. There are many this usable security and privacy is a huge area, right? So the problem we are working on is on image privacy. Okay. And this was motivated by the fact that, some of these services examples I have in the bottom might have gone into history right now, but looks like they're still popular. But it's possible because they change so often. Um, as a society, we take billions of images with the advent of digital photography. We don't have to worry about, picking a right shot. We are free to take as many photographs as possible and keep what we need and delete others. I have a feeling that most of you probably never had to deal with film cameras. Anybody in the audience um, who have, I mean, I would imagine faculty, but any students who work with film cameras? Uh, Anyway, when we had film cameras, there was 35 pictures you can take in a film roll. And so, and film rolls cost money, and developing those film rolls into photographs costed money. So we were judicious about, when to take pictures, what picture to take, and so on. But digital photos don't cost anything to take a picture. You can store as long as you have storage on your phone or device. Printing costs, right? Same as before, but not a lot of cost to take. And so we take billions of images and we store them typically in cloud-based storage spaces. And the advantage of using these cloud-based storage systems is they provide large amounts of storage that's typically not available on your mobile device. You can access them from anywhere, and you can share it with people. And so I don't have to make a large case for these services. People use them, and these are for photo storage, but services like Instagrams and Snapchat, you share them with friends immediately, right? The privacy challenge with this situation is that they provide a very convenient service, but they are not that private, or not necessarily, depends on the service, because providers like Google and Apple have access to your photos in these scenarios. Okay. Things have changed since we started this work. I mean, providers have been doing different things, but if you look at it, trusting the provider to preserve or defend your privacy is not always wise, because these are some articles from around um, mid 2010s, where providers that we trust our data with exploit that data for their own benefit, right? And these are some old paper clips, but you can see these kind of things coming up all the time, right? Um, and even if a provider has good intentions and wants to keep your data private, there could be external actors that could hack into these systems and gain access to your images, right? Um, and so there were breaches, um, in a while ago. I think this was the um, 2014 breach, but there have been more like this since then. A lot of pictures of celebrities from iCloud got hacked because hackers were able to get into it. So what I'm trying to convey is that when we upload pictures to an online storage service, we are exposing ourselves to a privacy risk, either from the providers themselves, if they have rogue employees, or providers themselves have an incentive to look at your images, or providers don't have good security mechanisms in place and they become vulnerable to external factors. A new emerging threat at the time, and this has only gotten worse since then, is that just based on pictures that you post onto social media, because AI and machine learning techniques have gotten so much better over the years, you can scrape. This particular paper was talking about how you can just scrape pictures posted on the internet and are able to predict relationships between people based on pictures. So they did a retroactive study, right, to see if their model works. But the key component of this work is this highlighted one, face recognition, right? Automatically recognizing faces and images. And at the time, 2010, 2009, 2010, if I'm remembering correctly, was the inflection point where machine learning models um, gotten better than humans at detecting fake faces and images. And by 2014, 2015, with um, deep learning models, I mean, there was an explosion about this capability, right? So that's the idea that if you post pictures, people can infer a lot more than just what's in the pictures. And this is an example from that paper showing, depending on how close people are standing, what are their expressions and body language, they were able to predict relationships. Um, this again is a news article from 2020. We are 5 years later. This is no longer news for you all. This is probably a matter of practice. Um, when we are out walking on the streets, anybody can snap a picture of us. And so that's not prohibited. When you're in public spaces, people can take pictures of you. But in the past, they didn't have, I mean, if somebody wanted to take that picture and find out more information about you, it would have taken them more effort. Today, Clearview was one example in 2020, but now, Bing has image search and Google has image search. You can put a picture in any of these image search services and they will pull up other pictures of you from the web. So it just makes it so much easier for people to capture a picture of random people on the street and learn more about them in an automated fashion, right? You didn't have to do a lot of work. So this again, the advent of machine learning or neural networks is a huge privacy challenge. We are not able to address all of these in the two talks, but I'm going to touch upon a couple of these challenges in the talk today. Okay. So the problem is for these models to learn, they have to learn. If for them is where you put an image in there and they can search through databases to find your other images, they have to learn. But the problem is services, which we saw some of them. I'm using them as examples. I don't know details of any of. I'm not making comments on any individual services here, but you can imagine services like Google, Apple, Facebook, and any of the big tech companies that provide image storage have access to users' images for learning purposes. And I'm not saying anything new. If you're using Alexa, the Amazon voice activated control, or if you're using Siri and Microsoft has their own thing, all of them, when you sign up, ask you permission to use your voice samples for training their models. In fact, Siri fell behind because they weren't doing that in the past. They weren't using user inputs to train their models or improve their models, whereas Alexa was using them. And so, Alexa made huge progress in terms of recognizing different accents and such, whereas Siri lagged behind. So I'm not saying something new. People have access to your data and they're already learning on them, right? ChatGPT is learning on all the data available to it. Okay? And my point is they have enough resources to learn models about you. So with this, I'm going to jump into the two parts of the talk. Just making a time check. The first part is about designing an encryption system that still allows you to browse your images. We call it thumbnail preserving encryption system. The other part was exploring whether adversarial perturbations can be used as a privacy defense against neural networks. But before I go further, I wanted to check if there are any questions. I can see a broad view of the room, so I may not be able to see if you just raise your hand. If you can speak up, I think that might work better.
Yeah, if anyone has a question, feel free to just speak out. So, looks like there are no questions at this point.
Thanks, James. So let me dive in. The first piece of work, thumbnail preserving encryption, is led by my former PhD student, Kimya Tajik. And this is my other PhD student, Akshit, whose picture I forgot, but I'm just pointing out since I seem to have I had a lapse there. But this was published in 2019, and we have a follow-on work that we are working to submit right now. But this is a really cool idea. And one of the solutions for the image privacy problem of storing images on, photo storage services is that, hey, we know how to encrypt. We have good encryption techniques that work very well and are integrated into most of our tool chains. So why not just encrypt the images before you store them to Google, and then we don't have to worry about or again, I'm using company names as examples. I'm not trying to have an opinion on their security posture, but whether it's Google or Apple Cloud, if I encrypt and post, then there is no privacy risk. If somebody hacks Google or Apple or anything, my images are still encrypted, and I don't have to worry about Google and Facebook or Meta, whatever those companies are about learning. And so here is an example. How many of you recognize this picture? Anyone? A few. It's a scene from a TV series called Friends that probably has reruns going on, but hasn't been on air for a while. It was a very popular series, maybe about 20 years ago. Anyway, my PhD student was a big fan, so if you'll notice, rest of our paper uses pictures from that series. Anyway, so this is Rachel, Jennifer Aniston from Rachel is the character name in the series. And so if I take this plain text, apply a standard encryption technique AES, this is what the ciphertext would look like, right? More or less. So it just looks like noise, right? Which is great. For privacy, perfect. I can put as many of these pictures into whatever image storage service I have, and they won't be able to learn much about that picture from the ciphertext. Okay. I'm assuming the terms plain text and ciphertext are you're familiar with those terms. Okay. Ciphertext is just an encrypted text. And so this is how your Google or Drive, if you're using, or Box, or wherever you're storing your images, looks like. So I've just put pictures of the some of the co-authors on the paper in here. And if I go back to my Drive to look through my album, this is how it would look today on the left side. On the right side is how it would look after I've encrypted them. So if somebody broke into this, they won't get much other than whatever they might learn based on the names of the images, okay, at the bottom. But this solves the problem of privacy. The challenge is that it's private, leaks no information, but less usable. Because when you go back, maybe you want to look at pictures from 3 years ago from a birthday party that you took. And so you go back to this folder, and then all you see is a blob of these noise blocks. And you can still, of course, if you decrypt them, you will see them. But unless you decrypt, or you can maybe infer something based on the names, you can't really browse through your album and say, let's say I want to pick 5 pictures that from that party or from that event that I want to print. So I'll have to download all the images locally and decrypt them, and then decide which 5 to pick. So this is not, usable or efficient, right? Less usable and inefficient. So in 2015, one of the co-authors on this paper that I'm talking about, he was the first one to propose this idea. They proposed the idea of thumbnail preserving encryption. And the idea is simple, is that instead of making encryption look like white noise, maybe we can leak a little bit of information, sufficient enough for us to browse our images, right? And so here is my co-author, Charles, and his idea was, okay, this is the original image. I'm going to invent a new encryption scheme that's going to make the ciphertext look like this on the right side. So it is leaking some information. For example, I mean, if you see the original image, you can probably infer more, but if you didn't know anything about the original image, you can still see there is probably a blue background, and maybe there is a wall behind, whatever, right? So it leaks some information, but not a lot. But the key idea here is that if you've seen this image before, then by looking at this thumbnail, your memory will be jogged to what that original image was. And that's the key part. So this paper is so fascinating because it has elements of cryptography, it has elements of usability, and it has elements of how you remember things. So psychology and memory, right? And so that's the idea that, oh, I'm encrypting the image. It's leaking some information, but there is a balance. It's not leaking enough information for somebody who's not authorized to look at and infer something, but it's leaking just enough for somebody who's the owner of the image to kind of be able to recall what the image looks like. Okay, that's the idea. And their idea, Charles's work was a very a simple but elegant idea to do that, to achieve it. So I'm going to show one layer of the picture. I mean, there are multiple layers, but let's just assume, for our discussion's sake, that a picture is just a grid of pixels. Okay, and each pixel has a value from 0 to 255. So these are the values of pixels, and this is a 4x4 grid. And so I have in here I have a 8x8 pixels in this image, right? But I'm just taking a 4x4 grid here. And the thumbnail is basically a low resolution version of this picture or this image, where I just average. I can pick any block size. Here I'm picking a block size of 4x4. I could have picked a block size of 2x2, right? Or 3x3 doesn't really work because it's not, it's okay. We don't need to get into those nitty-gritties, but I could have picked 2x2, or 4x4 works. And so all I'm doing is I'm taking all these 16 pixels, computing an average, and representing the average as 1 pixel. So I've scaled down the resolution of this image from 8x8, which is about 64 pixels, to just 4 pixels. So I'm reducing the amount of information available, right? That's essentially what a thumbnail is. So what Charles's idea and Wu Chi-Feng's, when they proposed this idea in 2015, is, hey, if all I need to do was to preserve the average, then if I just permuted the pixels in this block, the average doesn't change because the numbers I'm adding up are the same, just different order I'm adding that up in. So the average doesn't change. So that means the thumbnail doesn't change. And so that was it. The simple initial proposal for thumbnail preserving encryption was you pick some block size in the image and just permute the pixel values. And you will have some jumbled up image. Hopefully, there is some knobs. And like what block size you pick impacts how jumbled up the image is. If you take a really small block size, then you don't hide much. You can still see the details. If you take too big a block size, then you lose all detail. Imagine if I took the entire image into one block. That means I get one pixel information, nothing useful for me to be able to recognize the image. So I'm not getting into those details, but the idea is that if you permute the block, you preserve the average, but you can jumble the details, right? So the idea is that you'll end up with something like this. Here is the original image. If I compute a thumbnail, which means I'm averaging blocks of pixels, I will get this low resolution image, which is grainy. I can't get a lot of details other than perhaps there is a person, perhaps that person is female, and that's about it. If I didn't know anything about the context prior. And so if you apply something like permutation, this is not quite exactly the permutation that I'm showing above here, but it looks something similar. And basically, this is what you saw here. It is just with permutation. Okay. And so you'd get something like this for the full image ciphertext. But it turns out, since all you did was just permute the pixels, the thumbnail will be exactly the same. So the idea is that if you're just looking at the thumbnails in your drive, you can still browse through your images and distinguish between two different images. Okay. So that's the usability part. Okay. So the problem with this scheme from 2015 was that it's actually leaking the actual values of pixels. And so we wanted to create an encryption scheme that would have similar properties, but it doesn't leak the actual values of pixel, right? And we call it ideal thumbnail preserving encryption because it's not leaking the individual pixels. And this is the idea that you take an original image, you apply an ideal thumbnail preserving encryption, so you will get something like this, but it doesn't leak the original pixels either, but you still get the same thumbnail. Okay? And so how do we do this? And so I'm going to spend, I'm already about 30 minutes. James, were you intending a 40-minute talk or a 50-minute talk?
Yeah, 15 minutes is fine. Yeah, there's no rush at all. So how much time do you need?
All right, thank you. And so our idea was, instead of just permuting the pixels, if all I care about is making sure the sum remains the same, and permuting the pixels is actually leaking the pixel values, then the next logical step is to say, hey, for a given sum, once you pick a 4x4 or whatever block size you want, for a given sum of the pixel values in the original image, there are many, many, many number of combinations of pixel values that will all add up to the same sum. You can do this, simple exercise I'll give you with 2 pixels, and let's say each pixel can have 0 to 9, right? And so if I have 2 pixels, 5 and 5, and so the sum is 10, I have 10 different ways of generating those 2 pixels that sum up to 10. I can have 1 and 9, 2 and 8, 3 and 7, and so on, right? Actually 5, because it doesn't matter the ordering. Actually, yeah, you can swap the pixels. The order does matter at least from an image perspective. So you do have 10 combinations, right? So that's the idea. So that means for these 16 pixels, each of them can have a certain value. I'm only showing 4, but the idea is that there is a large number of combinations of pixels that will add up to the same value. In this case, I'm just calling it X. Okay. And so if I can just randomly pick one of those other variations, randomly I'm going to qualify. randomly and uniformly, means no bias on which of those combinations I pick, right? If I can do a uniformly random selection, I'm good, and replace this block with that block. Awesome, right? I have a scheme where I'm not leaking the pixels, but the sum of the pixels and the block remains the same, so the thumbnail looks the same, but it's very different from the original picture, right? I mean, that's the idea. The problem with this is that for me to be able to randomly pick one of those slates of combinations, I should first be able to generate them. And it turns out that even for small block size, so if you look at just 2 by 2 pixels, I have and so I'm the number of possibilities of combinations of 2 by 2 pixels, of course, depends on what those pixels are, but the max case is, I think, 2 power 17, if I'm not, I forget the base of this log, whether it's a log 2 or log E. Then I don't remember if it's a base 2 log or natural log right now, but either way, it's exponential, right? It's either 2 power 17 or E power 17. If I do this block 4 by 4 for a particular value of some x, which is about half of the max possible, the number of combinations that I have of these panels is exponential in 2 raised to the power of 83, which is huge. Generating that many different things and picking one of them is impractical. Okay. I don't know what kind of year all of you are in, but are you familiar with the cryptographic strengths of keys and sort of like, you know, how big? So for example, are you familiar with how big 2 power 80 is? Do you have a sense? Any comments anybody wants to share? Anybody? I mean, I'm sort of lost a little bit because I don't know which year of the program you're in terms of I might be just assuming you know this stuff and I'm zooming through. So if it's not, stop me and I'll be happy to dive in.
Yeah, we have a whole range of years here, so.
Okay. So just to make sure we're level setting, right? I have to go back and I might be overshooting myself here a little bit, but just to get a sense, if I have 2 raised to the power of 128, right? That's if I'm not mistaken, that probably is larger than all the atoms in the universe combined or something like that, I would imagine. I have to go back and check what that number is, but we are talking about very large numbers here. In fact, in cryptography, how many of you use or are familiar with AES, Advanced Encryption Standard, that we use? Yeah, I see some hands up there. What key sizes do you use for your keys? 128, 256, probably, right? 128 is the minimum, I think, now, and maybe we're already up to 256. I haven't checked NIST recommendations of late, but the idea is that they pick those key sizes, and if you say I'm going to search through the key space of 256 bits, it's huge, right? It's really not feasible to search through the space. So those are the size of numbers that we are dealing with here, right? They're huge numbers. They really have, you can't imagine even storing those numbers, right? Not the individual number, but elements, that many elements in a computer, right? So we can't store these. So I have to generate them somehow randomly, one instance of this gazillions of possibilities. And I should be able to come back from that, right? So we come up with this scheme, which is fascinating from one perspective. I mean, all modern ciphers are substitution and permutations. So this is also a substitution and permutation operation, right? Combinations of them. So here we said, okay, we do what's called a neighborhood-based substitution. What that means is, so recall, for a block size of 2 by 2, it's huge. But for a block size of 2 or a block size of 3, actually 2 by 2 we can manage. It's 2 power 17 is not too bad. 4 by 4 gets harder, right? So if in this example, I'm showing blocks, neighborhood blocks of 2, So I'm just taking these two pixels that are neighbors to each other, and I'm substituting them with a different pair of pixels, but that add up to the same value, right? So I'm taking 20 plus 50, and then I'm splitting them as 10 and 60. I could have done, 30 and 40, whatever, but I'm just uniformly randomly picking a different pair that adds to the same value. And I call it the substitution step because I'm actually taking two pixels and I'm substituting them with different pixels, okay? And then once I've substituted all of them, for example, 150 plus 40, I've substituted them as 140 and 50. 70 plus 30, I made it 10 and 90. So, and I picked the combination uniformly at random, right? And so I finished substitution everywhere in the blocks, and then I permute the blocks. Permutation means I'm just changing their position in the block, right? So this 10, instead of being the top one, now is in the middle somewhere. This 150 being on the edge is now somewhere here. So I'm doing a random permutation, right? And now I do, now that I got a permutation, now I smidge these two pixels. And then I smidge these two pixels and I smidge these two pixels together, right? And so our encryption scheme basically is substitution, permutation, you get a new image. You do substitution, permutation, you get a new image, and we just keep doing this one after the other, right? And so the idea, if you think about it conceptually, is that I'm taking pixels and I'm mixing them, right? That's but at all times, I'm preserving the sum for a block. Why? Because if I smidge these two pixels together, substitute them, I preserve their sum. These two pixels summed up to 70. Now these two sum up to 70. I haven't changed that. If I smidge these two pixels together, yellow, 730, 100, and I'm summing. So I have not changed the sum of the pixels in this block after my substitution step. And we know already from Charles's scheme from 2015, permutation obviously doesn't change the sum either. So even though I'm mixing the pixels, I'm not changing the sum in that block of pixels, right? And that's the key. So the idea is that I'm mixing them really well, and I'm deliberately using the term mix, and you'll see why. So I'm mixing the pixels really nicely, like kneading a dough. I'm kind of getting in there and getting them all mushed up, but I'm not changing the sum. So at the end of it, this is how they look. So if I took the first picture and applied this technique, so this is how that looks. And now you might be saying, hey, it is actually leaking in some information. I can control the amount of information it leaks by varying the block size. If I increase the block sizes, I will leak less information. If I reduce the block size, then I will leak more information. So that you can fine tune. But here you can see it is leaking some information. For example, I would imagine you could tell in all of these images there is a portrait. In some of these images, you could probably tell this is a woman versus a man gender, male versus female, and so on. Maybe you could tell somebody is wearing formal clothes and so on. So it's leaking some information, but you can tweak that. And so that's the essence of the scheme. That hey, now I'm hiding some essential details, but I'm able to browse through my images because I can still browse through these images because I've seen these images before and I can recall. And that's the psychology part or the memory part. There was a study a long time ago, and I'm blanking on the name of this phenomena, but the idea was if you've seen an image before, you will need, I think, a lot less information to recognize that image again versus if you haven't seen the image before. And the idea was, I think I have to go back and look at the details, but if you've never seen the image before and they give you an image of a person, the minimum number of pixels you needed in the face is X amount for you to be able to recognize that person if you knew that person. But if you've seen that image before, it's much, much less. And that's the phenomena that we exploit in the design of this scheme, that as an image owner, I can recognize these images with much less information than somebody who hasn't seen these images before. That's the idea, okay? And so proving this security in just, how I decide to smudge, like how do I go from 2050 to 1060? And when I permute, I have to be able to if it's encryption, then I have to be able to recover or decrypt the message. So I have to be able to undo the process, right? So I have to do this in a way that I'm able to undo this whole mixing that I did, which is actually hard. So we use AES as a primitive in itself for that mixing, and I won't go into the details. If somebody is interested, I have a link in the beginning of this presentation, and I can share these slides or the link. You can look up the paper for the details. But is the scheme secure? And so, without getting into the details of the proof, the way to think about it is, if I were to take a set of pixels and I'm able to compute all other combinations of pixels that add up to the same value, and there'll be many, 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 many of them. If I'm able to uniformly at random pick one of those other combinations and swap it, then I'm doing it in a way with there is no bias, right? I'm picking any one of those possibilities equally likely, and I replace it, which means somebody who's trying to break the encryption don't have an advantage of, oh, on what basis can I go back from that selection to the original one, right? There is no the original values other than the sum, nothing about the original pixels is influencing which set I pick, right? So I want to be able to pick uniformly at random. And so the idea is, if for every block of pixels, when I finish this, encryption process, the probability that I picked one of the possible combinations with equal probability across all possible combinations, if I can keep it uniform, then I have a good scheme, because it'll be harder for somebody trying to break this scheme to reverse the scheme without knowing the secret key. And the way we model this encryption scheme with this substitution permutation rounds, intuitively, the reason I was using mixing time is that if I mix it well enough, turns out that I will end up with a uniform distribution on how I'm picking the final pixels in the block. And so the question is, so then how many rounds do I need to mix it to get that uniform distribution? And so we model this as a Markov mixing process for the proof. How many of you are familiar with Markov chains or heard about Markov chains? Not many. I can only see four people, and they're shaking their heads. So a Markov process is where state spaces. You're familiar with the concept of a state space? Where an algorithm is moving from one state to another state, or where some process is moving from one state to another state, right? So basically, if you think about a state space, if I'm in state X, if the probability of me going to any of the other states in the state space is just dependent on my current state and nothing to where I've been before, it's called a Markov. There's no memory. My next action is purely determined based on my current location, right? Markov chain. So we model this encryption scheme using a Markov process, and we prove that the number of rounds that we needed in the encryption scheme for a uniform distribution is equivalent to something called a mixing time of a Markov chain. And so there is this equation. The thing to remember is that the epsilon is the security parameter I'm interested in. How strong do I want my scheme to be? And typically, I think in our paper, we set epsilon to be 2 raised to the power of negative 80. So very, very, very tiny error. And the way we think about that error is that fraction is that's the chance of an adversary breaking my encryption scheme, right? So I want to set it to 2 raised to the power of minus 80. So this epsilon is fixed by me. This omega, if I'm remembering my Greek letters properly, it represents the number of states. So it actually is determined by the pixels, number of pixels in my block and the values. So I can compute that based on what I'm encrypting. What I don't know is this lambda star. This lambda star happens to be the second eigenvalue of the probability transition matrix. Actually, of a transition matrix that is related to the probability transition matrix of the Markov chain that I'm modeling. And computing that is hard because, like I mentioned, the state space is huge. What's the state space? The state space is all the possible values of pixels that sum up to the same to the same sum. So if I take 16 pixels, there might be 2 raised to the power of 83 different ways of adding the pixels to the same sum. So that constitutes the state space. So there's lots of states. But at least I know what it is. I can compute the number. I can't compute all the states, but I can compute the number of states. But this lambda is hard to, turns out lambda star is hard to compute. There is no known way, at least we couldn't find any in the literature, for a matrix of our size, huge matrix. So what we end up doing is we prove that lambda can only be between 0 and 1. That's the values it can take. So if lambda ends up, 0, then log 0 is 1. We're good. Then the number of rounds I need is just based on the values I already know. If, on the other hand, lambda is 1, log 1 goes to infinity, and then we have a problem. It's 1, it goes to 0, and this value goes to infinity, and we have a problem. So we just model saying, hey, assuming our scheme can be implemented, even though we don't know lambda star, so I don't know how many rounds before I achieve uniform distribution, I can just check how things look. So about half at lambda 0.5, and if I take a reasonable enough block size, maybe 32 by 32, I am at 2 raised to the power of 8, 2 raised to the power of 10, by 1,000 rounds. If I take even a bigger block, then maybe 2,000 rounds, right? And so on. So, and we have, we've done lambda star calculations for smaller matrices, and we noticed that in all the smaller ones we computed, it really never crossed half. So, but we don't know if larger matrices it might go. But so what this means is our scheme is asymptotically secure. Like if I do enough mixing rounds, then our scheme is secure. But we couldn't pinpoint the exact number of rounds needed for our scheme to be secure. A follow-on paper did it. I think they fixed it at about 3,000 rounds or something like that, and they used a different proof. Okay. Any questions on this so far? Okay. No questions. All right. So now the question is, okay, you have a fancy scheme. Yeah, you kind of hand waved and convinced us it is secure. So is it any useful, right? So we did a user study, and again, as I mentioned, you'll see pictures from that TV series Friends. And so we've encrypted them using our scheme with different block sizes, and actually did a user study, asked users to see if they can recognize these scenes. In what our observation from that small user study was that you can browse your images in Google Drive or Box or Dropbox, whatever it is, using thumbnails at a similar efficacy level as if you're looking at regular images. In the thumbnail resolution we picked was such that if you gave it to Google Vision API, it couldn't recognize this scene. Okay, so it's not a perfect validation, but at least at the time we took Google Vision API was the most advanced Vision API at the time available openly. I think Clarify came a year or two later, but we give to Google Vision API. Google Vision API doesn't recognize the scene. So we pick that block size and use that in our encryption scheme and give it to users. And if they've seen this scene before, they can recognize it. They can distinguish it between other scenes. If they haven't seen it, obviously they won't. But here we are modeling the owner's usability, right? Right now, we are actually undertaking a study. We finished the study. We're analyzing the data where we are also analyzing how much information is leaked to non-owners. So we also modeling non-owner users in our user study right now for an extended version of this scheme. Okay. So that's the story for thumbnail preserving encryption. And there are some weaknesses to that I'll come to the end and point out. But any questions, thoughts before I continue? I'm already at 50, so maybe I can skip the second part. I'll just give you a high. I mean, there are two schemes here. I'll skip the second part and then go back to future work. But I wanted to just convey the idea of the second part of this talk, not the details, not the schemes, but just an idea, right? And so we talked about how these convolutional neural networks, came on the scene mid 2010s and changed the image recognition, or image, face recognition, image recognition tasks. Pretty high accuracy even for thousands of classes. The first time, basically, these models beat humans right around that time. And so, but the key thing, and you might have already seen this. How many of you seen these examples before? So this is just one example. There are many, many such examples. So these CNNs or machine learning models are fantastic at recognizing images. And actually, I've seen a demo in a XAC, a security conference many years ago, where they said, we have CAPTCHAs. How many of you seen those curly, messed up words that they'll ask us to, oh, can you spell this word and I'll admit you as a human into the site, CAPTCHAs, right? And so there was a Chinese version of CAPTCHAs with the Chinese characters. And at least for a human, for me, it was so hard with all those lines and zigzagging lines and stuff to recognize those things. And they showed, a neural network, deep neural network model was able to break a Chinese character CAPTCHA very easily. In fact, the CAPTCHAs were designed with the principle that these tasks are easy for humans, but hard for models. But, the models have gotten so much better that they're breaking them. But even though the models have gotten so good, this is the original image of the panda on the left side. If you gave it to a model, this was, a publication first this pointed out in this paper, 2014. The model would say, hey, this is the picture of a panda. And it had 60% confidence, roughly 57. And yeah, good. That's pretty good. It's a picture of a panda. Excellent. But what they found out is that if you just tweaked this image by adding this noise, and look at this noise, I'm actually adding it 0.007 times. So it's a very tiny fraction of this noise. Then you'll get this picture resulting on the right side, which to our human eyes hasn't changed much, right? It is still a panda. But if you ask the same model now, if you gave this image to the same model and say, hey, what is this picture? It'll say gibbon with 100% confidence. And you can vary this noise to make the model probably pick anything you want. And this is a huge vulnerability for CNN or machine learning models, because by adding a small imperceptible noise, you are changing the output of the model. And this is what, when people talk, oh, AI is coming, is doing fantastic stuff, ML models are doing fantastic stuff, but there are challenges. This is the brittleness of these models is one challenge. And you probably noticed when you're playing with ChatGPT, it gives incorrect answers very confidently. And the problem here is that you can actually induce it to give you wrong answers on purpose. Okay. So and so people did, this is a digital attack where I'm adding this noise, and people actually showed it in the real world. You take a stop sign and you just add a little sticker on the stop sign at the bottom. You walk on the street, just paste a sticker on the stop sign, and they've showed if you had a car like Tesla, these days a lot of cars have these automatic street sign recognition programs. and they showed they can make the car think it's not a stop sign, but a 55-mile speed limit sign. And now that's dangerous, right? So if you have these cars running around this with vision model, and you run around, I'm hoping none of you would do this, but if people run around sticking these stickers on stop signs that for normal human eyes don't change the function of the sign, but for this vision cameras makes a huge difference, right? And makes them think it's something entirely different. So anyway, that's the vulnerability. What we were trying to do is this, can we leverage this for privacy? That means when I'm posting my pictures onto Google, can I add this imperceptible noise and upload it? If a Google rogue employee or a Box rogue employee looks at them, yeah, my privacy is lost. But assuming companies are not being blatantly violating your privacy by humans looking at it, but they're happy to run models on them, our hope was, can we make the model mislead the models, right? And it turns out we can. I'm going to skip all over. There were other papers that did this, but I'm going to skip this. So this is one scheme that we proposed. That's the original image. The middle row is the perturbed scheme, perturbed picture, and the above one is the recovery, when you want to recover your original image. And you will just store these. So you can still browse through these images, but the idea is that if there was a machine learning model running on your inbox at the storage provider, they will recognize this as differently than what it was. Okay? That was the idea. So we show that we have an efficient way to learn, and we have parameters that can, make it easy for you and so on. So I have two sub schemes. I don't need to get into the details. This was the stop sign example I was talking about. That somebody just painted love or hate or whatever, and then there are others, right? Just tiny stickers. You put them, and then it changes the output from a stop sign to a 45-mile speed limit sign from a car's perspective. Okay. Anyway, so I have a second scheme. I'm just going to show you the final output of the second scheme. Yeah. So this is Matt Damon, but I have this scheme which doesn't even need CNNs. It's just an overlay scheme. And so you can take that image and store the bottom images in your storage service, and they would have a hard time recognizing that person. Whereas you as a human can tell it's Matt Damon. So that's the idea, right? Easy for humans, hard for models kind of idea. So we were using perturbations for privacy, so Google Vision basically fails to, their efficacy comes down to less than 20%. Right. So that's what this work is showing here. I'm going to skip to the back just as to what's coming next. The other thing I didn't show you in the talk, I mean, there's a lot more happening in AI machine learning space, and lots of challenges in security with those models. But one of the things that AI models, machine learning models have also gotten very good at is that if you give a thumbnail a low resolution image, they can super resolve it. You see this in movies where there'll be a surveillance camera, and then they catch a picture, and the cop or the boss says, "Hey, zoom in," and they keep zooming in 1,000 times, and then suddenly you see a clear picture. I mean, it's only possible in movies. You can't zoom in that many times, right, on a low grainy picture. But if you have a machine learning model, it can try to imagine, fill in the gaps, and super resolve it. So it's actually taking this thumbnail and super resolving it. While this is not exactly as this picture here, but it's good enough. If you give it to a machine learning model, I bet this would be classified as this user, right? So if you give it to, like, you can think about it as a sketch by a witness, right? And then police will be able to, okay, this person maybe is likelihood. So it's still, they do a decent job. They can super resolve this grainy middle image into this image on the right, which means thumbnail preserving encryption has a problem, right? And actually recent paper showed that they can take these thumbnails that are encryption scheme leaks, and they can super resolve them. And I'm like, yeah, that's true. That's a problem. So you'll have to then make this even more grainier. And now you're playing this cat and mouse game. So one of the things that we are doing is my PhD student Arizu, who did the perturbation work, showed that, you know, just like you can add a tiny amount of noise to a detection scheme and make it recognition scheme and make it, give you the wrong answer, you could do the same thing for super resolution networks. You can add a tiny amount of noise to this and make the super resolution go completely different direction. And it turns out that I don't even have to add the noise in the middle picture. I could add it here. And it survives the encryption, but the super resolution process doesn't destroy the noise, which is interesting. So that if I added, sorry, I misspoke. It doesn't change the super resolution will produce this image, but this image will be produced with the noise included. So if I actually gave it to a face recognition, it won't recognize the right person. So this is where we say adversarial images against super resolutions are free, because if I learned against the original image, that's enough, right? So that's one solution. Maybe not completely satisfactory, but that's one. The other one is we have a new scheme called enhanced TPE. Instead of just leaking a some preserving thumbnail, I can control what I leak more flexibly. So we are working on that submission right now. Other future works for some of you looking for interesting research topics is all I've done in terms of evaluating the privacy of these schemes is empirical. I've given it to Google Vision API or Clarify or some vision model and said, hey, vision model cannot recognize after this, or user studies. But there is no formal way of quantifying how much privacy we are getting it, right? So those are the challenges remaining in this work. Anyway, I'll stop now and take questions.
Okay, well, thank you very much, Rakesh. Does anybody have any questions? Let's see. Yeah.
So, Bernie Van Lee here, I'm one of the co-PIs on this project. So in the thumbnail preserving encryption, you've encrypted the image to where the human can realize which image it was. But how do you get it back from that to the original image if if just a small amount of noise is causing some software not to be able to recognize it? How do you get it back?
Yeah. So thank you for that question. So let me go back. I can. So this is the substitution permutation process, right? So I didn't catch your name. So my apologies. But the idea is that this entire process is reversible, because the way I do the substitution, for example, the way I decide that I went from 20 to 50 to 10 to 60, even though I'm trying to mimic a completely uniform coin toss, that's the idea. That's the ideal way to do this. In practice, I'm actually using a pseudo-random coin toss determined by a security key, right? And so since it's pseudo-random and it's seeded by a security key, I'm able to know that coin toss and reverse it. So that I didn't get into that detail here, but that's the thing. To make sure my substitution and permutation are reversible, I'm using AES as the one that's producing the seed. So AES itself is a permutation scheme, right? So it's reversible. So I'm using that. So I can actually recover. Let me go back. So the bottom is the original, the top is the encrypted version or the thumbnail, similar to thumbnail. I actually can recover back from that thumbnail to the encrypted, to the full version, because I'm using this reversible. It's not So I'm only, how do I say, computationally uniform probability, not information theoretically. So it's not true uniform distribution. It's a uniform distribution that no limited computation limited adversary can distinguish. Does that answer your question?
Yeah, I think you're saying that there's some logic in how the permutations are done,
Yes.
and how that logic to begin with, we can reverse it. Is that
Yeah. So
correct?
yes, exactly. Ideally, if I did fully uniform, I won't be able to reverse it myself, right? Because it's coin tosses, and unless I store all the coin tosses at every point, which is what I have to do, right? So for example, let's say there are 100 different possible pixel palettes I can pick from for a given pixel palette. And I do a random choice and I pick 99. And so I have to remember that I picked 99 for this and then, way to go back. So, but if I remember that. And the way I remember that compactly is by using the pseudo-random function with a seed. So I only need to remember the seed. I don't need to remember the entire tossings of the coins.
Okay, so you're storing the results of the tossings, and that's somewhere, and that can be reversed.
Yeah. So the way I'm storing that, so there is this concept of pseudo-random generators in crypto. So their entire purpose is, hey, I'm not a true random number generator, but I appear to be true random generator. Nobody who has limited computation can tell the difference, right? Because most of modern cryptography that we use is computational security, which means it's saying that, hey, I'm not saying that nobody can break this scheme. It's no adversary that has a limitation on their computation can break this scheme. If you give them unlimited computation, they can break the scheme. They can tell that, hey, this is a random distribution and this is not or this is a random number generator and this is not a random number generator, or this is a pseudo-random generator. But if you have limitations on their computation, they can't tell them apart, right? That's the premise under which most modern cryptography operates that we use every day. So it's the same idea that I'm pretending to choose these things, these substitutions uniformly at random, but I'm not really. I'm using a pseudo-random generator, which I can reverse if I have the secret key.
Very interesting.
Yeah, and for the second part, for the perturbations, it's just an addition. So I have to store the perturbation. Otherwise, I can't reverse.
Right.
So there is some external storage I skipped over. So keeping a perturbation per image is a storage burden. So I wanted to learn one perturbation that I can apply to multiple images. So we call them universal perturbations. So that's one of the innovations we do here.
Very interesting work. So can someone hack into your perturbation generator and then regenerate?
So one of the things I showed is that there is actually a challenge with this perturbation. I can generate a universal. So two problems. If I have to generate a unique perturbation for every image, which I can, but it's very expensive, right? Because I'm now running multiple neural networks to generate that unique perturbation. So I said, oh, I don't want to do that. I'm going to try and learn a universal perturbation that I can apply for, let's say, 100 images or 200 images. So I amortize the cost. Sorry, I'm going to show this example here. But the problem is, if I'm using the same perturbation for multiple images, it turns out that I can take the original image, take an inverse of the image, subtract it from the, I don't know the original image, right? But I can, if I know, hey, these are 10 images that all have the same perturbation on them, I can use some averaging or filtering techniques to extract the perturbation out, even though I don't know the original images for those perturbed images, right? So this is the perturbed image. I don't have any original images, but I can use some filtering techniques to extract the perturbation out of that using multiple such perturbed images. And then I can then subtract the perturbation out of this image. And I won't get exact clean copy of the original image, but I can recover enough, right? So it turns out, even though I'm able to generate a universal perturbation, which is a good thing on its own, from a privacy perspective, if the adversary knows that I'm using the same perturbation across multiple images and they have access to those perturbed images in a Google storage scenario, the adversary will have, they can recover. So then the question for us was, can we generate unique perturbations per image without the cost? And so that's when we go into the second scheme where we don't need any learning, and I'm able to generate a unique perturbation for every image. And it's also very simple, if you have time, I can give you an overview, but I don't know what's next on your schedule. So
Yeah, our next speaker actually isn't going to be here, so we have time.
okay, and if the students don't think I'm killing them, I'll take less than 2 minutes to give you an overview of this one. It's also a cool idea. I like cool, simple ideas than anything complicated. So there is this idea. Hold on, let me go back instead of transitioning. Okay. So this is just overlaying one image over the other. These are called transparent images, overlaying images. And so here is an image of a human face, and there is a car, and in between everything is a combination of those two images, weighted addition, and we call it overlaying. There was a paper in 2017 that showed that if you just weighted overlay images in video, you can make the automated video transcription go off. Right? Automated video transcription, what it's doing each image, and in a video, it's looking at each frame and annotating that frame. So you can make that, so we get the idea from them. Oh, overlay images can be used to fool recognizers, right? But the challenge is, if I use, the same overlay image in multiple images, then there is a technique called blind signal separation. It's a signal processing technique. It's able to restore the original images to some extent. So you can't just, use the same overlay image either, right? So our idea was, take a small set of images, whatever. You pick random images. I'm showing you some here, right? A small set of images, and given an input image, and a secret key, let's say the input image has an ID, whatever. So I'm using the ID as a salt, so to speak. I'm gonna use AES and AES encryption scheme with the key and that ID to pick two out of those images at random. And so this images that I picked here depend on the ID of the image, right? And then I break those two images into smaller blocks and permute them. Okay. And then I overlay those both those images with this input image. So it's a very simple idea. I'm demonstrating it with using a smaller number of examples, right? And so it turns out that with very little effort, one secret key and a bunch of images, in this case, I probably had 10 images, I can create a unique overlay for any input image, right? I can, I don't have to store it either. All I need to store is these 10 images and the secret key, and I can always generate a unique overlay for. And for decryption, I can regenerate that unique overlay for subtraction, right? And so I have in my paper a lot more examples of these images. Maybe I can open up that paper. Let me see if I have it handy here. It seems in the presentation itself, I don't have too many examples for you to look at. But that's it. It's a very took us a couple of years because we were so hell-bent on using CNNs to create these fancy perturbations and so on. And then we said, okay, it's cool idea. CNNs are awesome and everything, but in terms of actual meeting the practical requirements, they're not that awesome, right? So let me see if I can find an image to share, or if I only have Matt Damon. Yep, apparently we loved Matt Damon enough that that was only picture that made it into the paper. But I can show you a progression, perhaps that is different. Because I know we have an image repository that we have a lot of them. Okay, so I'll pull this up and see if it makes a difference. Let me stop sharing and share a different screen. Is this better? Are you able to see something?
Yeah. Could you zoom in maybe a little
A little bit more. Let's see if I can. I think that's the most it's going right now.
bit?
Maybe there is a different way to do this. Maybe if I do it, just share the window, maybe I have more control. Let me see. Yeah, probably. Okay, let me go back. So just as an example, these are the, you know, uh, set of overlay images that I used in our scheme. And essentially what we are doing, sorry for all the scrolling. I'll stop once okay, it's the same images. All right. Let me come back to the bigger version. Okay, so what we're studying here is that, hey, what's the block size that I need to make for the, so if you have a too big a block size, it's revealing too much. But if your block size is small enough, then it's creating enough fuzz in the face that the vision schemes are having trouble recognizing these things. And here, the number of keys, sorry, not number of images used for overlay. If I use too many images, so if you recall in the scheme, I picked, sorry.
See your screen right now.
Oh, I'm not sharing my screen. Oh, how about now?
There we go, yeah.
So here I picked two images from here. So that's the value of K. How many images am I overlaying the final picture with? And so it turns out if you increase the number of images you're overlaying it with too much, see, it's the same block size, but as the number of pictures that I'm overlaying with increases, the noise goes away in the faces because when I overlay too many pictures together, it acts like white noise, so you don't notice it in the picture. So you want to keep the number of images you're using low. So 3 is ideal. I'm showing 4 here and 2 here. So 3 is somewhere in between. In alpha is the weighting of the overlay image versus the original image. So if you have too much alpha, again, the weights on the overlays is reducing, so faces become clear. Whereas if you keep alpha low, then the weight on the image, actual image is lower, so it's kind of becomes harder for you to see and harder for the image recognition or face recognition algorithm as well. So anyway, that's the couple of years of fun we had. exploring how to improve image privacy while keeping it usable for end users.
Yeah, great. Any last minute questions before we let Dr. Baba go? All right, well, it doesn't look like there are any questions at this point, so thank you very much.
Thank you all for your attention. Thanks,
Yeah,
James. I'm gonna sign off now. Thank you all.
It's great. Yeah, thanks for joining us. Appreciate it. So, our guest from was originally scheduled to, like I mentioned earlier, couldn't make it. But we do have our 3 o'clock speaker who's able to join us early. So what we'll do, I know we've all been in our seats for a while, so let's go ahead and take a 10-minute break while we get set up here. Hopefully you don't mind waiting a little bit.
No, great.
Yeah, so take a 10-minute break, do what you gotta do, and then we'll meet back here. And then after this, we'll be done for the day. We can try to look at our computer.
That would be great, just because I have animation.
Yeah.
It was like heading towards us. Did you see it? Yeah. Because it's such a motion. So yeah, I like swinging my chair at all.